The answer is no. They do not communicate uniform risk estimates due to the implemented force-based quantities, such as PGA capacity over PGA demand in some of the guidelines. So we tried to remedy this by deriving a simplified pushover-based framework named PB risk for the estimation of seismic risk, which is expressed in terms of the mean annual frequency of exceedance. And this integrates the average spectral acceleration, which I will call average SA from now on, because it's a bit of a tongue twister at the end of a long day, as the interface between vulnerability and hazard. The third question was, can we estimate robustly and more efficiently the direct economic losses due to earthquake events? And you've guessed it, we derived a simplified loss assessment procedure termed PB loss, which integrates generalized story loss functions with the previous tool and framework for the direct estimation of seismic losses. These three procedures have demonstrated an acceptable trade-off between accuracy and computational demand, and most importantly, consistency and reliability. But what do they all have in common? The common factor was the SA average as the main intensity measure. It was always considered as the interface between hazard and vulnerability. The average SA was first introduced in the early 2000s as an efficient IM for response prediction. Ever since, many studies have pointed out its high efficiency, sufficiency, and practicality properties. It is defined as a geometric mean of the spectral accelerations at a set of oscillator periods of interest, considered to be appropriate for estimating multiple structural response metrics that are critical for risk assessment and loss estimation of the structure. So the question today is, can we derive reliable analytical fragility functions for the regional assessment of infilled RC frame buildings using average SA? To get started, just a bit of setting out the groundwork here through with general notions. So fragility curves or functions quantify the exceedance probability of any structural demand-based performance level or limit state as a function of the ground shaking intensity. This could be PGA, SAT1, average SA. Fragility functions are derived either analytically, empirically, heuristically through expert judgment, or via a hybrid approach. These fragility functions are typically represented via a log-normal cumulative distribution function with a median intensity and a logarithmic standard deviation or dispersion. A key step in the work that we're presenting today is the derivation. A key step in the derivation of analytical fragility function first requires the definition of building classes. Building classes and taxonomies must be defined using building attributes that are relevant to seismic vulnerability, such as load-bearing system, height, or date of construction. Taxonomies must also be simple to remain familiar and applicable to other users, but also comprehensive enough to maintain relevance in how they describe seismic performance of different construction types. Based on national census data for Italy, we have identified 4 building classes prominent within the regional building stocks, namely low-code low-rise, low-code mid-rise, moderate code low-rise, and moderate code mid-rise infilled RC buildings. These building classes were identified based on 2 prominent features, as you might have guessed, the number of stories and the design code level. After identifying our building classes, assessing the seismic performance of structures generally involves analyzing numerical models referred to as archetype building models. Archetype models are based on essential aspects, and these aspects should consider a wide range of key architectural features representative of the regional context and the corresponding design practices, the gravity and lateral load-bearing structural system, variability in material properties, occupancy type, intended use, building height, elevation, and plan configuration, etc. Therefore, for this study, we used the database of archetype building models for infilled RC frame structures, which was previously developed in previous studies. This database considers 2 temporal design practices, namely pre-1970s or low code, where buildings were designed to resist gravity loads only, with no consideration to ductile detailing, and post-1970s or moderate code, where seismic design was carried out with respect to the equivalent lateral force method, where a lateral force coefficient of about 7 to 10% was typically considered depending on the seismic zonation that we're in. And for this application, a seismic coefficient of 7% was considered. Numerical models of the archetype were developed in OpenSeas using a 3-dimensional lump plasticity approach. Empirical calibrations from various sources were employed to determine strength, deformation capacities, hysteresis parameters for different member types such as beams, columns, beam column joints, and infill panels. Following the definition of numerical models and before running any sort of analysis, probabilistic seismic hazard assessment must be carried out to characterize earthquake rupture sources at a specific site of interest and to identify the relationship between these rupture characteristics and the intensity of ground shaking via an intensity measure. OpenQuake was used to conduct PSHA, where the annual rate of exceeding an average SA level at a given site is obtained. In this study, the archetype buildings were assumed to be located fictitiously in the city of L'Aquila in Italy. And the most recent European seismic hazard model, ESHM20 short, was used with the site characteristics presented by Mori et al. To estimate the hazard curves for different definitions of the average spectral acceleration. Next, the derivation of fragility functions requires the ability to accurately quantify the exceedance of any structural demand-based damage state. Damage states are widely used in seismic risk applications to relate observed structural damage to consequences like building functionality, economic losses, and possible casualties. In practice-based applications, damage states are typically referred to as limit states and are triggered by several potential factors, both on a local and global level. This can be either global displacement-based, local deformation-based, or local strength-based criteria. For example, the Italian National Code, or NTC 2018, identifies 4 limit states based on the lateral capacity of the main structural system. Since the typology under consideration in this work is non-ductile infilled or C-frame buildings, these damage states are also impacted by the premature failure of the infill panels and the degradation in strength due to the in-plane, out-of-plane interaction. However, in this study, we focused mainly on the in-plane failure of the masonry panels, and experimental tests carried out by Surya et al. Demonstrated that for infilled or C-frame buildings, the initial damage states are governed by the in-plane drifts sustained by the infill panels. These corresponds to story drift value of 0.16 and 0.29 for the operational and damage limitation limit state. To account for this, a hybrid definition of damage state thresholds was adopted in this study, where the findings of Surya et al. Were adopted for the operational and damage limitation limit states, and NTC 18-based guidelines were adopted for the definition of the life safety and the collapse prevention limit states. An additional collapse limit state was considered, where complete structural collapse is expected. That is taken to be when 5% story drift is exceeded in nonlinear dynamic analysis. And so a series of multiple stripe analysis using hazard consistent ground motion records at discrete intensity levels was carried out to individually characterize the nonlinear dynamic response of the archetype buildings. But before that, hazard disaggregation analysis following PSHA was carried out to identify the most representative rupture scenarios for a given IM and return period. A suite of 25 records per intensity was selected using the toolbox for ground motion selection and processing EasyGM. And this was carried out considering 5 conditioning periods, T star, for average SA, which were in the range of the geometric mean of the first mode periods of vibration of each building. 9 intensity levels corresponding to return periods of 22 to 4,975 years were analyzed to characterize structural response from initial damage all the way to global structural collapse, while keeping the scaling factor threshold for record selection at 2. The analysis was carried out. However, a drawback of multiple stripe analysis within this context and this application is that each archetype building model was evaluated using a slightly different definition of average SA. To remedy this, we've opted to use a single definition of the conditioning period for buildings belonging to the same class. This enables us to characterize an entire building under a single definition of average SA. As a result of the building grouping, results of MSA carried out on individual buildings would change given the shift in the intensity measure definition from multiple definitions of average SA to a single one. And therefore, new spectral intensities should be identified. And we try to do that without rerunning the analysis by simply calculating the intensities from the spectra of each individual gram motion record. And no changes to the EDP values were necessary. As such, the results of the multiple stripe analysis highlighted in the figure to your left would transform into a banded cloud of results similar to those achieved following cloud analysis, as shown on the figure to the right. The results are still largely hazard consistent, but alternatively, to avoid this recomputation of multiple stripe analysis results, a more direct approach could be adopted by selecting gram motion records for multiple stripe analysis in terms of the conditioning period of that building class. Now, to identify the median intensity and associated dispersion corresponding to a demand-based threshold for a single building case, our application becomes similar to that of cloud analysis, where a linear regression in the log space is carried out to identify an IM given EDP relationship, and the median intensity is obtained by intersecting graphically the regressed line with a vertical line representing the demand-based threshold and reading off the value on the y-axis. The associated dispersion, or in this case, the record-to-record variability, is simply the error in the fitted regression. Now, on an asset class scale, the previous exercise is repeated until all median intensities corresponding to all the damaged states for all of the buildings are collected. The seismic intensity of a building class for a given damage state is now simply the mean of individual seismic intensities at that damage state. As far as uncertainties are concerned, the seismic performance assessment of any given structural typology requires due consideration to both aleatory and epistemic sources of uncertainty. In the study, the overall dispersion associated with the mean log normal fragility functions of each taxonomy was derived as per the law of total variance by considering the intra-building, inter-building variabilities, and in addition to the modeling uncertainty. The intra-building variability considers the overall record-to-record variability, and this simply becomes the arithmetic mean of the observed record-to-record variability of all the buildings within a class, and is therefore a constant value since the error associated with the regression is itself a constant value. The inter-building variability is simply put the deviation of individual median intensities of each building within a class from the mean seismic intensity for any given limit state. So it's basically how far are the medians with respect to the mean, with the mean intensity that is characterizing our building class at that particular damage state. And the last source of uncertainty is associated with numerical modeling and the parameter values used in the modeling process, which can be related to material property, geometric configuration, and other numerical assumptions. To quantify the propagation of modeling parameter type uncertainty to the overall dispersion, a value of 0.34 was assumed according to a study conducted by O'Reilly and Sullivan for 2 to 6 story infilled RC buildings. After identifying the key components of fragility functions, analytical fragility functions can now be derived following the assumption of log normality, which implies that the IM values of ground motions causing damage state exceedances are log normally distributed, which is a common assumption that has been demonstrated in various studies throughout the literature, and the functions are illustrated on this slide. Verifying analytical functions with past earthquake events is a crucial step in the development of these functions in earthquake engineering. And so the verification process aims to assess the robustness of what we just derived in casting future damage predictions. To do so, empirical fragility functions obtained from observed damage after the occurrence of a significant earthquake event is surely invaluable. So, empirical fragility functions, similar to analytical ones, are models derived from pairs of observed damage and intensity data for buildings and infrastructure. On the x-axis, we indirectly have the intensity measure values at points of interest, which are obtained either through field surveys or numerical simulations using ground motion models. The y-axis indirectly relates to the damage data that is collected for a group of surveyed and spatially distributed exposed assets. Additionally, verification events should be statistically suitable and significant. This means that a wide range of ground motion intensities and scenarios should be covered to ensure the robustness of fragility functions across different conditions. And in this study, two seismic sequences were considered. The first being the magnitude 6.2 Umbria Marche earthquake of 1997, which in its aftermath, unfortunately, took the lives of 11 people, left hundreds injured, and at least 80,000 displaced. The second considered event is the 6.3 L'Aquila event of 2009, with almost 308 fatalities, left 1,500 injured, and rendered almost 66,000 displaced, and cost $16 billion in economic losses. So the first step in deriving empirical fragility functions is to map the intensities associated with the rupture scenario that occurred. For this purpose, ground motion fields, or short GMFs, are derived following an earthquake event using ground motion models, or GMMs. GMFs associated with significant events are very important to our application as they provide, and for further applications actually, as they provide assessments of potential damage and community exposure. GMMs, ground motion models, provide a mean of predicting the level of ground shaking and associated uncertainty at any given site or location, and they are efficiently used to estimate ground motions for use in both deterministic, probabilistic seismic hazard analysis. The limitation, however, is now some ground motion fields are available through institute services such as INGV, USGS. However, their limitation is that they're only available in conventional IMs. This means PGA, spectral acceleration at 0.3, 1 second, and PGD, which are traditional IMs when we're looking at the universal building codes, but here we're looking at average SA, and this work is still on the frontier of, let's say, science. And so for this application, we need average spectral acceleration-based ground motion fields to validate what we just derived analytically. So two approaches exist for the estimation of empirical average SA values. Either the direct approach, which is a prediction via the derivation of a ground motion model from a strong motion data set, or the indirect approach, which makes use of peer-reviewed ground motion models for spectral acceleration to predict the distribution of average spectral acceleration. Given the joint log normal distribution of spectral accelerations at different periods for any given scenario, and the assumption of log normality of average SA distribution, the mean and variance of the logarithm of average SA can be indirectly estimated using the following equations. And so if we dissect the mean of the logarithm of average SA into multiple spectral acceleration values, we will refer to the GMM that is proposed by Bindi et al., which was used to evaluate these spectral intensities, as it was derived to estimate these spectral intensities at distinct periods ranging from 0.04 to 2 seconds. And the GMM also allows for the estimation of ground shaking intensities, such as, again, PGA and SAT, corresponding to magnitude range of 4 to 6.9, which our events are between these bounds, and considering distances of up to 200 kilometers. The prediction using ground motion models generally, and Bindi et al. Specifically, is based on an earthquake magnitude, source to site distance, local site conditions, and fault mechanism functions. But before the application of any ground motion model to produce ground motion fields, careful comparison of observations to various numbers of standard deviations on either side of the mean prediction is necessary. And to help account for this deviation, a new technique titled ground motion model conditioning can provide additional constraints on the ground shaking estimates in the region that is affected by the earthquake. And that is done using the ground motion recordings from station, or what is termed as ground truth. And the conditioning of the ground shaking is based on the methodology developed by Engler et al. 2022, which preserves the partition of the within event and between event residuals, thus enabling a more accurate propagation of the uncertainties through a Monte Carlo simulation approach. So for each IM of interest, mixed effects residuals are computed using the following formulation, commonly referred to as residual partitioning, where the between event residual is recomputed using the recorded data and reinserted into the equation above, and the GMM becomes an event-adjusted ground motion model that we can now use to simulate realistic intensities given the rupture scenario that has occurred in the past and following the applied constraints. Mu IM and delta B are now grouped in what is commonly referred to as an event-adjusted mean, and delta W represents the residual between the observations and the event-adjusted mean. The GMM conditioning may not always inflict significant changes on the non-conditioned GMM, yet it still remains as a suitable step to carry out to inject some reality through instrumental recordings into the prediction. Moving on to spatial correlations. Spatial dependence among ground motion typically impacts predicted consequences to spatially distributed assets. This correlation considers the spatial dependence in the joint probability distribution function of an intensity measure given a rupture scenario. And it was observed through many studies that considering spatial correlation yields the most accurate estimates. Hence, a model that does not account for spatial correlation may imply that larger than median motions would occur at individual locations if considered independently. And the spatial correlation model for the average SA that was derived by Hersey and Miranda in 2021 was adopted in this study. Now, several phenomena associated with earthquake rupture and wave propagation can produce these spatial correlation in the within event residuals. This can be due to the simplicity in the source description of ground motion models, site effects, geomorphological conditions of the considered regions, etc. Having assembled the key components for generating ground motion fields, the intensity is at each site within a controlled polygon or grid, and for a given rupture event are simulated using a multivariate normal distribution for the log normal of the intensity measure, in this case, the SAs. Conditional on the rupture I and site J, where tilde n denotes that the logarithmic of the IM, in this case, the spectral accelerations, is a multivariate normal distribution parametrized by the mean vector M, which is a vector of the predicted spectral accelerations that we got using our conditioned ground motion model, and the covariance matrix sigma, where tau represents the inter-event variability and phi represents the intra-event variability, and R is the spatial correlation matrix that we've calculated in the previous slide. Now, the ground motion fields corresponding to the two case study sequences were derived, where the average SA fields are plotted alongside the epicenters of the earthquake events considered within the sequence. And these intensity fields represent the mean ground shaking intensity corresponding to 10,000 simulations that were carried out, demonstrating the ground motion fields for the L'Aquila event and for the Umbria Marche event. I deserve the water break. Now, the second component of empirical fragility functions is to assemble empirical damage observations corresponding to the considered event. This data represents an invaluable source of information. And over the last 50 years, a notable amount of data relevant to post-earthquake damage to existing buildings was collected following earthquake events in Italy. This data was stored in a database of observed damage called the ADO, or DADO. And DADO is an IT platform and database which includes information on the structural characteristics and the observed damage to buildings inspected after the most relevant seismic events that occurred in Italy after the Friuli 1976 earthquake onwards. The DADO database includes information on 2,164 RC buildings following the Umbria Marche 1997 event, and information on about 8,500 RC buildings following the L'Aquila 2009 event. The damage state data were collected according to the IUSS survey, which is a subset of the European macroseismic scale, or EMS 98. IUSS identifies four damage levels four damage states composed of 6 damage levels, ranging from D0 to D5. And before 1997, damage data were collected mainly with what regards to the state of the vertical structure, such as the Umbria Marche event, for example. And following 1997, new extensive damage were included in that survey to reflect on the state of non-structural elements that can be present in a building, such as infilled panels. However, in order to adequately validate analytical fragility functions with empirical fragility functions, an equivalency is required between the hybrid limit states that we've established in the previous section and the IUSS damage states to help provide a more comprehensive comparison between empirical and analytical fragility functions, and to be able to say that we're comparing apples with apples in this context. And therefore, some assumptions must be made. And in the study, the hybrid limit states, which were adopted in the analytical fragility functions, were related to the IUSS damage state as illustrated in this table. For example, we assume that D0, or undamaged limit state, corresponds to the operational limit state in the hybrid approach. D4, for example, corresponds to the collapse prevention limit state in the hybrid limit state, and so on. Having characterized the information required for both axes on the fragility function, we now possess all the information required to fit our empirical fragility function. And we're only missing the techniques for deriving such empirical fragility functions. Now, given the availability of building-to-building data, we assume a Bernoulli distribution for characterizing the random component of the statistical model. This is basically the component that is corresponding to the y-axis on the fragility function. And YIG, in this case, given IM, indicates whether an asset I is in damage state J. And the outcome of Bernoulli distribution is a binary outcome, meaning that for a certain damage level, all exposed assets with an observed damage level, that is D less than DI, will have a probability equal to 0. For a certain damage level, all exposed assets with an observed damage level D greater than DI will have an assigned probability equal to unity. This adoption of the binary Bernoulli distribution allows for avoiding aggregation of damage data, which may introduce uncertainty and overlap in the fragility functions. Now, for the derivation of fragility functions, a further step requires an appropriate statistical model and fitting technique to approximate the observational data as a function of the ground motion severity or intensity measure level. As such, the cumulative log-normal distribution, similar to that adopted in the analytical fragility function, is adopted for describing the probability of exceeding a damage level as a function of the seismic intensity measure, where fragility functions are simultaneously fitted via a maximum likelihood estimate approach, where the optimal parameters, in this case, the median intensity and the associated dispersion, result from maximizing the logarithm of the likelihood function. So this slide shows a bit of a graphical explanation on how to apply the Bernoulli distribution, where we basically dissect our damage observation into zeros and ones, and then we fit that log-normal CDF using maximum likelihood estimation. And the end result is empirical fragility functions, as you can see. In this case, it's for Umbria 1997 and L'Aquila 2009. Now you might be thinking, we've identified 5 damage states. Why are we seeing 4? This is the result of not having enough significant damage data corresponding to collapse in the database, unfortunately, so we cannot draw any conclusions with regards to the ultimate limit state, that is collapse. As far as verification and conclusions, the first major takeaway of this study was the reduction of uncertainty in fragility functions that was clearly demonstrated. This is crucial for improving the accuracy and reliability in seismic risk applications. Reducing uncertainty was demonstrated to be achieved using more efficient IMs, such as average SA, and choosing appropriate IMs is highlighted to be beneficial, as the choice directly influences the robustness of the fragility functions. So the influence of the IM choice on the associated uncertainty is demonstrated in this figure, where we can see the efficiency that average SA has demonstrated with respect to other conventional IMs, such as PGA and SAT. These correspond to the beta or the dispersion associated with the empirical finding or the empirical fragility functions corresponding to other IMs. The uncertainty values refer to, again, dispersion in the empirical FFs, and a major improvement in efficiency was demonstrated, particularly at moderate to high damage states, such as damage limitation, life safety, and collapse prevention, where the concentration of damage initiates and propagates, and where we tend to outgrow the elastic response. An acceptable prediction in the estimation of the seismic intensities associated with the serviceability limit states, in this case, SLO and the damage limitation limit state, was observed. However, a consistent overestimation of the seismic intensities associated with the remaining damage state was observed. Now, this can be due to many sources of error. Damage accumulation in buildings following earthquake sequences is a cause. The damage data was collected following and after the conclusion of the earthquake sequences in both Umbria Marche and in L'Aquila. This meant the data itself was not time-stamped, which means that everything was collected after buildings have accumulated a lot of damage from the previous events within those sequences. Another source of error could be the assumptions associated with the anchoring period for the empirical fragility functions. We cannot accurately identify the conditioning period of a building if you see it just outside the window. We cannot tell. But we are assuming that our analytical fragility functions and the empirical ones, they have some sort of a correlation between their periods, which may result in errors in the prediction. The uncertainty in the damage state definition between empirical and analytical fragility functions is a big assumption. And this requires a lot of accuracy and a lot of guts to actually come up with this assumption. And in my opinion, this causes a lot of the discrepancies that we find in the two fragility functions, empirical and analytical. Last but not least, the bias in the data collection itself, due to the differences in damage state perception between one expert and another, can be another source of uncertainty. One may consider, one may be overestimating, one may be underestimating the extent of damage that has been collected for the same building or for different buildings. And so in this case, we are injecting a bit of variability through bias in our results. With regards to conclusion, fragility functions are used worldwide for single building and regional seismic risk and loss applications. Previous studies have opted to use conventional IMs such as PGA and SA for the derivation of analytical and empirical fragility functions. The novelty in this work was to present analytical fragility functions that were derived using the average spectral acceleration. And these functions considered all sources of uncertainty, record-to-record variability, building-to-building variability, and modeling uncertainty. The empirical fragility functions were derived using novel SA average-based ground motion fields that were conditioned on the station data to account for the ground truth and damage observations. The average SA did offer a more reliable characterization of structural vulnerability, which was highlighted by the low associated variability compared to more conventional IMs. For the case of the empirical fragility functions, the analytical fragility functions consistently overestimated the seismic intensity across the range of structural response or across damage state. And this opens up a perspective for future work. What can we do to figure out what is going on? What is this discrepancy coming from between analytical and empirical fragility functions? Some items that we can carry out could be sensitivity analysis on the period range that is associated with the average spectral acceleration, simulation of ground motion fields and testing using more ground motion models. In this study, we've only used a model that seemed to be representative of the Italian tectonic regime, which has been the Ital, but it is worth experimenting with more ground motion models. Now, running nonlinear time history analysis, accounting for damage accumulation, which means running our archetype models in a main shock aftershock sequence. But this changes the scope of this study. We're not looking at state-dependent or we're not looking at state-dependent fragility functions in this case. And so the characterization of a more importantly, the characterization of a more adequate relationship between code-based limit states and empirical damage state is a must. We have to be able to find some sort of harmonization between the two scales so that we can say that we're comparing apples to apples. Because despite of all the hypotheses and assumptions that we made throughout this study, we seem to be a bit comparing apples and oranges. Leave you with the references that were used in this study, some useful links with regards to the building models, the toolbox for ground motion selection, OpenQuake, and the database of surveyed buildings. Thank you very much. Looking forward to your questions.
Okay, so thank you, Mouayed, very much for a nice presentation. Do we have any questions from anyone? Also online as well, if you want to leave a comment or something. Yes, you'll have to speak loudly so everybody can hear you, though.
First of all, and then you have done 3 parts that each could have been 1 PhD on its own. So I'll start from the beginning. Let me say that taxonomy or infilled RC building. To what extent do you think we can generalize this to RC building without any RC building have infilled? So what you have done with taxonomy, to what extent it can be extrapolated or it can be used for RC buildings, let's say?
First of all, thank you very much for your kind comment. And I think to answer your question, you can go as detailed as you can. It depends mainly on your application, let's say. Now, RC buildings is a huge building class. If we start disaggregating, we will end up with so many subtaxonomies at the end. Let's say RC buildings with shear wall, with dual systems, RC buildings with moment resisting frames, infills, no infills, heights, period of construction, level of design code. So there is no extent to how much we can go, but it mainly depends on your application. In my application, I was looking at infill RC frames. So I was trying to dissect that big umbrella of building class into what I considered most prominent within the building, within the regional building stock that I'm interested in.
Yeah, I should have mentioned this. The same initial data that we have, I mean the census data.
Mm-hmm. Yeah.
In that case, we don't have the information about if it is moment frame or if it is, we just know that it's us. So
you'll also know from the data that you have, the damage data. There's no point in fitting fragility. Well, there's no point in trying to compare fragility functions you develop with a model on your computer if you've got no empirical data to compare it to. You see.
So the
Sorry.
empirical,
Yeah. No,
so
you
the
go.
empirical data, what Jared's trying to say is that the empirical data that is in that database of observed damage does include infills in it. And we're trying to match analytical to empirical here. So empirical is our ground basis. The taxonomy is purely, its definition is purely empirical, what we have. If the damage survey said, oh, there's an infill wall here, there's not in other structures, this is what we're looking at. This is how we're trying to pinpoint that exact building class that we're trying to look at.
Thank you. But one part of the vision that you showed in your cloud, but do you use any any formulation or how do you come up with that modified regression?
Going back so many. So that regression is basically a linear regression in the log space.
The first part, yes.
Right?
The last part, it's not.
So you see the black line and there's a blue line that is a bit deviating,
Yes.
right? That is called a modified cloud analysis, where you take into account the collapse cases in your regression now. This is mainly done by applying a logistic function and getting your probability of collapse to be integrated by considering 1 minus the probability of non-collapse. There's a mathematical formulation that was proposed by Jalayer et al. on that specific topic. I wasn't the one that came up with this, and the reference is at the end of the presentation.
Yeah, do we have any other question or comment from anybody else now that Mouayed is nice and warmed up? I can ask you a very general question that maybe will provoke an answer. So you did obviously a lot of stuff. I mean, 3 different major topics, right? So which was the most difficult one for, say, the implementation of this, and what would you do differently if you did this again, say?
We're talking about all the topics
Any of it.
within this particular or
yeah.
the whole thing?
The last hour.
The last hour. I would say the empirical data, the processing of empirical data was the most difficult, in the sense that first it was outside my comfort zone. I've never looked at empirical data before. I was an analytical guy just 3 years ago, 1 year ago. And so looking at empirical data, trying to make sense of what we have, trying to come up with these assumptions that you've seen that there's still some refinement that we can do. Empirical data is still the ground truth that we have, and it's the information that we can rely on. But there's so many assumptions that go along the way that you have to prove at every point of your, well, let's say now my academic career. So trying to justify these assumptions was, I would say, the most difficult part. And so my answer in simple terms would be the empirical derivation.
And if you were to do all of this again, would you do anything differently?
Oh, no,
No. It's all perfect.
no, it's all perfect. I'm so proud of my work. Yeah.
Okay. Any more questions or comments? We can have one more because then we have to close. But you sure?
Before you start, you need you find that has out there in terms of average population. Explain what was the relation before deciding which and how much dispersion of that. I mean, you looked at your taxonomy and then decided what would be my average spectra, then it has or because it might be different if you choose different value range or different angle different. What was your approach to define this?
The anchoring period.
First assumption before doing the analysis.
Okay, that's a very nice question. So when we started building this database of infilled models, a simple thing to do would be doing a model analysis, an eigenvalue analysis, where you get the mode shapes, you get the first mode period, depending on how many modes you have, how many modes you want. So that gives us an indication of what is the period that I am expecting that particular building class to be the first mode period. And so my assumption for the average or for any hazard curve, whether it's condition based on the anchoring period, would be that the results of a model analysis on analytical models. So for example, if my T1 in the X direction is 0.2, my T1 in the Y direction is 0.2, it means I have geometric mean of 0.2. I'll take 0.2, plug it in as my anchoring period. There you go. That's my starting point for building that hazard curve.
That's all the architects, or how you make them?
Now to explain more of what we did. So we actually ran a multiple stripe analysis on these archetypes before. So we actually had the information for all the individual buildings. So we had the T, the conditioning period, which is the anchoring period for the average spectral acceleration intensity measure. We've had that. So we are now able to do a simple PSHA, get our hazard curve, run motion selection, and do MSA. Now, when we reached this point of the work, we thought it's not ideal, as I mentioned, to represent every archetype building individually, because we're trying to aggregate everything in one building class, right? But we're also trying to avoid running extensive nonlinear time history analysis again, because in this database, we have almost 105 numerical models, and running every one for 9 intensity measure levels, 25 records per intensity measure level, accounting for the convergence issues that we have, it was not feasible to go and redo multiple stripe analysis. So what we did was consider the same multiple stripe analysis using the first mode, the hazard that we got from the analytical models, and try to condense it into one, let's say, taxonomy anchoring period that was around the geometric mean of the whole buildings within that building class, and just fetch the intensity measures, because now we're not looking at stripes anymore. We're looking, as I see, at like a fuzzy cloud of results. This is because not everything is scaled to that period anymore. And so it's easier to go and fetch the intensity measure level from the spectra rather than rerun. Nothing would change. It's more ideal, of course, to have, I'm not going to conclude that it's more ideal actually, but yeah, just to avoid running that multiple stripe analysis again. Go ahead.
No, go ahead, Basim.
Okay, you probably say that for the testimony, you use, like for the areas, for the anchored areas, you use geometrical mean of each structure. Why geometrical mean? Like why not average mean? Like because like since given that all structures are independent, why do you not? I'm not using the average mean or median, but using the geometric mean. Is there any specific purpose of it, or just like let's use average geometric mean?
I would say the funny answer to that would be why not? But in this case, it's still an assumption. There's no, let's say, direct purpose of why we use the geometric mean instead of the median or instead of the arithmetic mean or whatever. It was just an assumption. The geometric mean, as long as, the thing is, average SA should not be that sensitive, but I'm deviating here from your answer. Yeah, geometric mean, arithmetic mean, it's still, yeah.
Okay, I think we have to close it here because we're almost out of time with the booking of the room. So thank you again to everybody who's joining online, and thanks again to Mouayed for his presentation. And yeah, that's it until next time. So thanks again.